Analog electronics exercises. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I would like to invite you to observe the solution of 13 exercises involving diodes, transistors, and operational amplifiers. Let's go to the first exercise. Exercise number 1. For the circuit of the figure, state whether the diodes D1 and D2 are conducting or not. Alright my friends, this is the exercise. Let's go to the solution. For starters, a diode is going to be conducting when its anode is higher in potential than its cathode. When the cathode is higher in potential than its anode, it is off, not conducting, okay? Let's start by assuming that D1 is off and D2 is on. What does it mean? It means that the branch of D1 is going to be open, and in the branch of D2 there will be current, okay? Observe that as the left branch is open, ID2 is the only current passing through the 6 kilo ohms resistor, okay? ID2 is the only current flowing here. This part of the circuit is open and this part of the circuit has current, and ID2 is the only current passing through the 6 kilo ohms resistor. 3 volts divided by 6 kilo ohms, which is equal to 0.5 milliamps. Why did I not use 10 volts? Why did I use 3 volts? I used 3 volts instead of 10 volts because this source here is not participating in the circuit. The circuit is open here because we imposed the condition that D1 is not conducting. Then the only current comes from this voltage source here and passes through the 6 kilo ohms resistor. Alright my friends, and since the current through D2 is positive, the current through this 2 is positive. Can you see that it goes from the anode to the cathode? It goes from the anode to the cathode. The current is positive. Then the assumption that D2 is on seems to be correct. However, since the voltage across the 6 kilo ohms resistor is 3 volts, the voltage here, okay, the voltage here is gonna be 3 volts, okay? And the voltage here is gonna be 10 volts. And the potential difference, VD1, is equal to 7 volts, okay? We see that VD1 is 7 volts because its cathode is at 3 volts and its anode is at 10 volts. But then there is an inconsistency here, because if the anode of D1 is higher in potential than its cathode, then it must be conducting, and we assumed that it was off. Then there is an inconsistency there. Observe that it is not consistent with the assumption that D1 is off. Therefore, we must try another assumption. We are going to use another assumption. Firstly, we assumed that D1 was off and D2 was on. And we saw that there is this inconsistency here because the anode of D1 is higher in potential than its anode. Then it is not off, it is on. Okay? Then we are going to have to assume another situation to see whether the diode D2 is off and the diode D1 is on. Okay? Let's go and have another assumption. Now let's assume that D1 is on and D2 is off. Under this assumption, the equivalent circuit is this. This is the equivalent circuit in which D1 is on and D2 is off, okay? And as this branch here is open, the current that passes through the 6 kilo ohms resistor is ID1, okay? Since the branch on the right is open, ID1 is the only current passing through the 6 kilo ohms resistor. Thus, ID1 is equal to 10 volts divided by the resistances 4 kilo ohms and 6 kilo ohms. 4 kilo ohms plus 6 kilo ohms. Okay? Then the value of the current is 1 milliamp. Okay, my friends, the voltage across the 6 kilo ohms resistor is, let's calculate the voltage here. The voltage on top of the 6 kilo ohms resistor. This voltage is going to be 1 milliamp. The current that passes here, ID1, times the resistance 6 kilo ohms, and the voltage is 6 volts. Okay? We have here 6 volts, okay? And this is consistent with the situation in which D1 is conducting, because here we have 10 volts and here we have 6 volts. ID1 can be calculated as this as well. Another way of calculating ID1. ID1 is equal to 10 volts minus 6 volts divided by 4 kilo ohms. Okay? Then our assumption that D1 is on holds true. It is consistent with the observation of the circuit. Thus, VD2 is equal to negative 3. Okay, I have here 6 volts and I have here 3 volts. Okay, let's look at diode 2. The cathode is at 6 volts and the anode is at 3 volts. Okay, and the voltage is negative 3 volts, okay, because the cathode is higher in potential by 3 volts than its anode. The contrary should happen, okay, for conduction. The anode has to be higher in potential than the cathode, but we saw that it is the contrary. In reality, the anode, the cathode of D2 is higher in potential than its anode. Thus, VD2 is negative 3 volts, which is consistent with the assumption that D1 is on and D2 is off, since for D2 the cathode is higher in potential than its anode. Nevertheless, for conduction, the anode must be higher in potential than the cathode, as in the case of D1. In the case of D1, the anode here, the anode is higher in potential than the cathode, because here is 10 and here is 6. But for diode D2, here is 6 and here is 3. The opposite should be true for conduction, alright? So this is all for exercise number 1. Let's go to exercise number 2. Exercise number 2 now. We are going to work with the same circuit, but now we are going to assume something different. Show that the situation in which both diodes are off is not valid for this circuit. Okay, my friends, this is exercise number 2. We are going to assume that both diodes are off, that is, not conducting, and the exercise wants us to verify whether this is valid or not. Okay, If we assume that both D1 and D2 are off, that is not conducting, then the equivalent circuit is this. This is the equivalent circuit when both D1 and D2 are off. Alright? Notice that as both diodes are off, no current flows in any part of the circuit and the voltage across the resistors are zero. There is no current flowing here or here, okay, because the circuit is open here and here, because we have established that the diodes are not conducting, okay. There is no voltage drop across any of the resistors because there is no current, okay. Nevertheless, there is no voltage drop across the 4 kilo ohms resistors. Then, if there is no voltage drop across the 4 kilo ohms resistor, VD1 is 10 volts, okay? This voltage here is going to appear here, 10 volts, okay? Because there is no current, and as there is no current, there is no voltage drop, and thus VD1 is 10 volts, which contradicts the assumption that D1 is off, because the anode of D1 is higher in potential than its cathode. When this happens, the diode must be conducting, and we supposed that it was off, and in reality we discovered here that it is false. It has to be conducting because the anode is higher in potential than its cathode, okay? Which contradicts the assumption that D1 is off, for when VD1 is 10 volts, the anode is higher in potential than the cathode, which is the very condition for conduction, okay? Upon discovering that D1 is on, we return to the second situation of exercise 1. Back then, we observed that when D1 is on, the voltage across the 6 kilo ohms resistor is 6 volts, okay? Now that we know that D1 has to be conducting, okay? D1 has to be conducting. D1 is this. Here is 10 and here is 0. Let's suppose this, okay? Because here is 10 and here, let's suppose this point here is the ground. And it has to be conducting. There has to be a current here, okay? And it causes, observe, back then we observed that when D1 is on, the voltage across the 6 kilo ohms resistor is 6 volts, causing its cathode to be higher in potential than its anode by 3 volts. Okay? It's going to be conduct. Okay? It's going to be conduct. There is going to be a current here, and this current causes the voltage here to be 6 volts and here 3 volts. Okay? And in this way, we have proved again that the diode D2 is off, because we can see that its cathode is higher in potential than its anode. Back then in exercise 1, we discovered that when D1 is on, the voltage across the 6 kilo ohms resistor is 6 volts, causing its cathode to be higher in potential than its anode by 3 volts. When D1 is on, D2 has to be off, because the voltage is negative. The voltage here, this is D1. For the case of D2, this is 6 and this is 3, and the voltage here is negative 3 volts. And this and thus D2 is off as we previously assumed. D2 is off because its cathode is higher in potential than its anode, and this is all for exercise 2. Let's go to exercise 3. Exercise number 3 now. Show that the condition in which both diodes D1 and D2 are on is not valid for the circuit on the board. We are still working with this circuit here, but now we are going to assess the possibility of both diodes be conducting at the same time. Okay? This is the exercise. Let's go to the solution. When we assume that both diodes are conducting, we have the following equivalent circuit. This is the equivalent circuit when both diodes are conducting, okay? And using the nodal rule, we obtain that ID1 plus ID2 is equal to IX. Okay, the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. Okay, this is the nodal rule, in which IX is equal to 3 volts divided by 6 kilo ohms, which is equal to 0.5 milliamps. And we can calculate also ID1. ID1 is equal to 10 volts minus 3 volts divided by 4 kilo ohms. And this is equal to 1.75 milliamps. Okay? From this expression, we obtain that ID2 is equal to IX minus ID1, which is equal to negative 1.25 milliamps. Okay, we have found the currents. And what is the conclusion that we get? Since the negative sign means that ID2 flows in the opposite direction, that is from the cathode to the anode, which is impossible under normal operation, we observe that actually D2 is off, contrary to the assumption proposed by the exercise. Okay, here we have this diode D2. We are supposing that ID2 is flowing in the normal direction from the anode to the cathode. But as we discovered here, there is a negative sign, which means that in reality the current is flowing in the opposite direction from cathode to anode, which is inconsistent with the assumption that the diode is on. In reality, as it is not possible under normal operation, the current must not flow in the opposite direction, then the assumption that D1 is on is true, but the assumption that D2 is on is false. Okay, so D2 is off, contrary to the assumption proposed by the exercise. The exercise proposed the assumption that both diodes are on, but we discovered that in reality D2 is off. Alright, my friends, this is all for exercise 3. Let's go to exercise number 4. Now let's work on exercise number 4. Observe that it is a different circuit now. The exercise says, find the diode states for the circuit of the figure. This is the circuit that we are going to work on now. Let's go to the solution, my friends. Let's firstly assume that both diodes are on. That is, both diodes are conducting. In this way, the circuit becomes this. This is the equivalent circuit when we establish that both diodes are conducting, okay? What can we do there? We can apply another rule, okay? The sum of the currents that enter a node has to be equal to the sum of the currents that leave the node, okay? In this way, we say that I1 is equal to I2 plus I3. We are going to write these currents in terms of voltage and resistance. I1 we already know. I1 is 5 milliamps. I2 is Vx divided by 2 kilo ohms, and I3 is Vx plus 10 volts divided by 1 kilo ohms, okay? Observe that as the polarity here is inverse, when the polarity is this in this way, pay attention, when we have Vx here, the resistance, and we have a voltage in this way here, they subtract one from the other. It is Vx minus the voltage, Vx minus 10 volts. But here the polarity is inverse. It is not Vx minus 10 volts. It is Vx minus 10 volts. Negative with negative, positive. That's why we wrote Vx plus 10 volts divided by 1 kilo ohms. Alright, my friends, this is the nodal rule that we are going to use to find the value of the currents. Okay? And in this case, we want the value of Vx. And if we work on this, it's simple mathematics, we find that Vx is equal to negative 2 volts, okay? The value of Vx is negative 2 volts. As Vx is equal to negative 2 volts, the cathode of the one is higher in potential than its anode, okay? Vx, we assumed Vx to be this way. We assumed Vx firstly to be in this way. However, as we calculated, we found that it is negative 2 volts. This negative sign here says that in reality Vx is not like this. Vx is like this, okay? Causing the cathode of D1 to be higher in potential than its anode. And when the cathode is higher in potential than the anode, the device, the diode, is not conducting. It is off, okay? So the assumption that both diodes are conducting is wrong, okay? Because there is a contradiction here. We expect the anode of D1 to be higher in potential than its cathode for conduction, but we discovered that Vx is negative 2. Then the cathode is higher in potential than the anode. Then consequently we find that in reality D1 is not conducting. D1 is off. Alright? And now let's work with another assumption, okay? This assumption here is not valid because we discovered that they cannot both at the same time be conducting, because D1 is not conducting. Now let's suppose now that D1 is off here, Okay, this is going to be the equivalent circuit in which D1 is off. Okay, let's suppose that D1 is off and D2 is on. As the central branch is open, observe here that the central branch is open. The current of the source passes entirely through the 1 kilo ohms resistor. Okay, the current is going to flow in this way here, and we know that I D2 is equal to 5 milliamps. There will be no current in the central branch because the circuit is open. We assumed that diode D1 is off now, and we are assuming that diode D2 is conducting. Okay, the voltage drop across the 1 kilo ohms resistor is, okay, I'm gonna call it VR. VR is gonna be equal to the current 5 milliamps times the value of the resistor, which is 1 kilo ohms, and this is equal to 5 volts. Alright, my friends, we discovered that the voltage across the 1 kilo ohms resistor is 5 volts. As a consequence, ID2 is 5 milliamperes. We already understood this. Lastly, we observe that 10 volts, plus VD1 is equal to 5 volts. Okay? From this voltage here plus this voltage here, VD1 is here, okay, VD1 is here, okay, VD1 is here. 10 volts plus VD1, 10 volts plus VD1 has to be equal to 5 volts, okay? There is a loop there that we can use to understand the voltages around this loop here. 10 volts is pointing downwards, okay? You have to understand this, that it is pointing downwards. VD1 is this, and we have 5 volts in this direction because the current of the current source flows in this direction here. Then we have this equation here, and we find that VD1 is equal to negative 5 volts. And what does it mean? With VD1 equal to negative 5 volts, we conclude that its cathode is higher in potential than its anode. Okay? When we put the arrow this, we are supposing that here is higher in potential than here. But as we discovered the negative sign here, we understood that the cathode of D1 is higher in potential than its anode. Okay? As VD1 is negative 5 volts, we conclude that its cathode is higher in potential than its anode, thus causing it to be off, as we assumed. Okay? And this is all for exercise number 4. D2 is conducting, that is, D2 is on, and we have proved that D1 is off, that is, D1 is not conducting because the cathode of D1 is higher in potential than its anode. Okay, my friends, this is all for exercise 4. Let's go to exercise 5 now. Exercise number 5 now, my friends, Consider the battery charging circuit of this figure with Vm equal to 20 volts, R equal to 10 ohms, and Vb equal to 14 volts. Letter A, find the peak current assuming an ideal diode. Alright, my friends, we're going to assume that this diode here is ideal. And we are going to use this expression of the voltage of the power supply, okay? The peak current occurs when the sine wave source reaches its peak amplitude, okay? Vs is equal to 20 times the sine of Wt, and its peak value, of course, as the exercise said, is 20 volts, okay? Consequently, the voltage across the resistor is going to be Vm minus Vb equal to 20 volts minus 14 volts, which is 6 volts, okay? At that time, the sinusoid reaches its peak, the voltage across the resistor is 6 volts. Okay, my friends, thus the peak value of the current is, that's what exercise asks us in letter A, find the peak value of the current. Okay, the peak value of the current is I equal to 6 volts divided by 10 ohms, and this is equal to 0.6 amps. Okay, my friends, this is all for letter A. Let's move on to letter B. What does letter B want? Letter B wants us to find the percentage of each cycle for which the diode is in the on state. Okay, this is what we are going to do. Okay, the diode changes state at the instant in which, this is letter A, this is letter B. At the instant, Vm times the sine of Wt is equal to Vb. Okay, at the moment, the value of the sinusoid is equal to the value of the battery, the diode changes states. Okay, thus 20 sine Wt has to be equal to 14 volts, okay? And then the sine of Wt is equal to 14 divided by 20, which is 0.7. Now we are going to calculate the inverse sine of 0.7, okay? What is the angle which has this sign? Okay, the inverse sine is 0.7 is equal to 44.4 degrees. Okay, this is a very important result in this calculation to discover the angle, all right, in which the sine wave is equal to the voltage of the battery. We are what are the values in which sine Wt is equal to 0.7? We observe that this value is equal to 44.4%. Okay, so let's convert this angle to radians. 2 pi radians. 2 pi radians is equal to 360 degrees. X radians is equal to 44.4 degrees. Okay, this is a rule of 3 in which we find that x is equal to 0.775 radians. Okay, we are going to work with radians rather than degrees. All right. Does the diode change status when Wt? The diode changes status. The diode changes state when Wt is equal to 0.775 radians. However, we have to be careful to not forget this. This is the circle, and here the axis. Let's suppose that this angle here is Wt1, but we have another angle here with the same sign. All right, we have another angle with the same sign. We are calling it Wt2. Okay, and Wt2 is equal to Wt1. Wt1 is equal to 0.775 radians, and Wt2 is equal to pi minus 0.775 radians. All right, my friends, these are the angles that we are working with, the angles in which the diode changes state. Okay, thus T2 minus T1 is going to be equal to pi minus 0.775 divided by W minus T1. T1 is 0.775 divided by W. Okay? All right? We have W here. We simply pass the dividing, okay? We have W here, we simply pass the dividing. And then, if we manipulate, we find that this is equal to 1.591 divided by W. All right? And using that F is equal to 1 over the period, and that W is equal to 2 pi F, we can write this in another fashion. T2 minus T1 is equal to 1.591 period divided by 2 times pi, and this is equal to 0.2532 times the period. And what is the conclusion that we get from this? We conclude that the diode is on for 25.32% of the period, okay? 25.32% of T. We conclude that the diode is on for 25.32% of the period. That is, in each cycle, the diode conducts for 25.32% of the time. Okay, my friends, this is all for exercise 5. Let's go to exercise 6. Exercise number 6 now. The circuit of the figure is a simple voltage regulator. The voltage of the source varies from 8 volts to 10 volts, and the current of the load varies from 50 milliamps to 150 milliamps. Assuming that the zener is ideal, determine the largest value allowed for the resistance Rs so that the load voltage VL remains constant with variations in load current and source voltage. Also determine the maximum power dissipated in Rs. Okay, my friends, this is the exercise, and let's go to the solution. The breakdown voltage of the zener diode is 5 volts, okay? The exercise said that the breakdown voltage of the zener diode is 5 volts. That is, there will be current through the zener only if Vz is greater than 5. What does it mean? There will be current here, there will be Iz will be greater than 0 only if the voltage here across the zener, if Vz is greater than 5 volts, okay? The zener will conduct only if the voltage is greater than its breakdown voltage. Okay, my friends, this is the purpose of using a zener diode. We need to choose Rs, so the minimum value of Iz is 0. Okay, we are going to find Rs for the minimum value of Iz. The minimum current through the zener occurs when Vs is minimum and IL is maximum. Okay, the minimum current through the zener is going to happen when Vs is minimum, that is 8 volts. And in this way, IL is going to be maximum. We can write that Is is equal to Iz plus IL, okay? How do we calculate Is? I'm gonna label here VL. I'm gonna use this label just to facilitate our understanding. Is is equal to Vs minus VL divided by Rs, which is equal to the current through the zener plus the current that goes to the load. Okay? And in this way, the current of the zener diode is equal to Iz is equal to IL. No, Vs minus VL divided by Rs minus I load. Okay, this is the current of the zener diode. We wish the current of the zener diode to be minimum, and it occurs when the voltage VL here is less than or equal to 5 volts. Okay, so we wish Iz to be equal to 0. Alright? And substituting the values, we find that Iz equal to 0 is equal to Vs 8 volts minus VL VL is 5 volts divided by RS minus the current that goes to the load. The maximum value of the current of the load happens when IZ is minimum, okay? And the maximum value of the current is 150 milliamps. In other words, 0.15 amps. And using this expression here, we find the value of RS to be equal to 20 ohms. Okay, my friends, this is the value of RS when the Zener current is 0. Alright? Now let's work with the power dissipation. The maximum power dissipation in the resistance occurs when Vs is maximum. Okay? When Vs is maximum when it is equal to 12 volts. Okay, so the maximum power dissipated, P max, is going to be equal to Vs max minus VL squared divided by 20 ohms. Okay, this is the maximum value. This is the maximum value of the dissipated power in resistor RS. And substituting the values, we find that it is equal to 12 volts minus 5 volts squared divided by 20 volts, and we find that the maximum power dissipated in the RS resistor is 2.45 watts. Okay, my friends, and this is all for exercise number 6. Let's go to exercise number 7 now. Exercise number 7, the Zener diode of the figure has a neat current of 5 milliamps and a maximum allowed power dissipation of 300 milliwatts. The question: what are the minimum and the maximum load currents that can be drawn, keeping VO equal to 6 volts? Okay, my friends, this is exercise number 7. We have a voltage source, a resistance, the Zener diode, and a load. Okay, let's go to the solution. We know that the current through the Zener must always be between the neat current and the maximum current allowed. That is IZK, the neat current of the Zener diode, is less than or equal to IZ, and in its turn, IZ is less than or equal to IZ max. Okay? In which IZK is the minimum current to maintain breakdown. It is the neat current, and IZ max is the maximum current before burning the diode. Alright, we don't want to burn the device. Then there is a limit, and this limit is this maximum current. Okay? Therefore, we're going to use that IZK is equal to 5 milliamps. Okay? As the exercise stated that the maximum allowed power dissipation is 300 milliwatts and the voltage across the Zener has to be 6 volts, the maximum value of the current through the Zener is we're gonna use this data. The maximum value of the Zener of the current through the Zener is I Z max is equal to the maximum allowed power dissipation, 300 milliwatts, divided by 6 volts, because we want to keep this voltage. Okay, this is the voltage of the Zener. We want to keep this voltage and assess the current for the maximum power dissipation, and this is equal to 50 milliamps. Alright, my friends, the current leaving the source, I1 is the current leaving the source, okay? The current leaving the source is equal to, I1 is equal to 9 volts minus 6 volts, okay? Minus 9 volts minus 6 volts divided by 50 kilo ohms, okay? This resistor is 50 kilo ohms. 9 volts minus 6 volts divided by 50 kilo ohms is equal to 60 milliamps. Alright? And we can apply the nodal rule here. The currents that enter this node have to be equal to the currents that leave the node. In other words, the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. In this way, I1 is equal to IZ plus IL. Alright? What do we want? We want now to calculate the value of the load current, IL. The value of the load current, IL, is equal to I1 minus IZ. Okay? I pass this to the other side. It becomes that IL is I1 minus IZ. And okay, IL is equal to I1 minus IZ. Let's calculate the minimum value of IL, the minimum value of the current that goes to the load. IL minimum occurs when the current that passes through the Zener branch is maximum. Okay, so the minimum value of IL is equal to I1 minus IZ max. Okay, the minimum value of IL is the one in which when the Zener current is maximum. Okay, and this is equal to 60 milliamps minus 50 milliamps, which is equal to 10 milliamps. Now let's finish by calculating the maximum value of the current that goes to the load. The maximum value of the current that goes to the load happens when the Zener current is minimum. Okay, then I1 minus IZK is equal to 60 milliamps minus 5 milliamps, and this is equal to 55 milliamps. Okay, my friends, this is the minimum value of the load current, and it happens when the Zener current is maximum, and the maximum value of the load current occurs when the Zener current is minimum. okay, it is equal to the breakdown current. And this is all for exercise number 7. Let's go to exercise number 8. Exercise number 8 now, my friends. Find the value of ID for the circuit of the figure. And the exercise gave us this data here. Okay, let's go to the solution. Firstly, we need to identify what kind of transistor we are working with. It is the MOSFET, okay? This transistor here is the MOSFET, alright? And for the MOSFET, I'm gonna put it here, VGS less than VT, the device is in cutoff. What does it mean? It means that ID is 0. No current passes here. When VGS is less than VT, the channel is not open. Okay, now let's open the channel. To open the channel, VGS has to be greater than VT. This alone makes the device operate in the triode region of operation. However, when VGS is greater than VT, when VGS is greater than VT, and in addition to this, VDS is greater than VGS minus VT, the diode, the transistor is operating in saturation. Okay? This is the MOSFET, and these are the modes of operation. VGS minus VT less than VGS less than VT, it is in cutoff, nothing happens. VGS greater than VT, it is in the triode region. And in addition to VGS being greater than VT, if VDS is greater than VGS minus VT, the device is operating in saturation. Okay, my friends, this is how we understand the MOSFET. We are going to suppose at first, we are going to suppose that the MOSFET is operating in saturation, okay, and we are going to use the expression for the current in saturation, okay. Supposing saturation, the current ID is equal to a half of nu n COX W over L VGS minus VT squared. This is the expression for the drain current when the device is in saturation. The exercise said, okay, the exercise wants us to use K, and K is going to replace all this, okay, it is going to be K. And then the expression becomes ID is equal to K times VGS minus VT squared. Okay, my friends, easy. Let's go slowly to understand everything. From the negative 5 volt source to the ground, okay, here from the negative 5 volts to the ground, we have that negative 5 volts plus ID times 1 kilo ohm plus VGS is equal to 0, okay? Negative 5 volts plus this voltage drop is ID times 1 kilo ohms plus the voltage between the source and the gate. This is the gate here. The voltage between the source and the gate is equal to 0 because the gate is grounded, alright? Did you understand this expression? It is paramount that you understand this expression because we are going to use it from this negative 5 volt source. Passing through this voltage drop plus VGS is equal to 0 because the gate is grounded, okay? Using this expression and rearranging, we find that ID is equal to 5 minus VGS, okay? Okay? Now from the 5 volt source to the negative 5 volt source, we have that from here passing all the way to here, from here passing all the way to here, we have that 5 volts is equal to 1 kilo ohms times ID plus VDS, okay? 5 volts plus is equal to 5 volts is equal to this voltage drop plus VDS, which is the voltage from drain to source, plus this voltage drop here, plus 1 kilo ohms times ID and minus 5 volts, okay? This voltage here is equal to the voltage drop across this 1 kilo ohms resistor plus the voltage drop from drain to source plus the voltage drop across this 1 kilo ohms resistor minus plus this negative 5 volts. And manipulating this expression, rearranging and manipulating, we find that VDS is equal to 10 minus 2 times ID, okay? Alright, we have these 3 expressions here. We are going to use them to calculate what the exercise wants us to calculate. We can equal them, okay? We can equal this to this. It's then K times VGS minus VT squared equal to 5 minus VGS. Alright? And developing this expression, it is easy. I invite you to try it. Developing this expression, we find that VGS is either 3.76 volts or VGS is equal to negative 2.26 volts, okay? Which one to pick? Which one of these values we are going to choose to use? Which one to pick? as we assume the saturation, VGS has to be greater than VT. Okay? We assume the saturation. Okay, this is cutoff, this is triode, and this is saturation. We assume the saturation, and in the saturation region of operation, VDS has to be greater than VT, has to be greater than VGS minus VT. Okay? As VT is 2 volts, the only solution that satisfies this condition is 3.76. Then this is not correct. The only correct is this expression here. Okay, my friends, let me raise the board for some room because I'm gonna need to write more things, but keep in mind these expressions here because we are going to use them. Okay, now that we've established that VGS has to be 3.76, now returning to the equation of ID, the equation of ID that we had here, we find that is equal to 5 minus VGS, which is equal to 5 minus 3.76, which is equal to 2.24 milliamps. Alright, my friends, this is ID, this is the value of ID for this current here. For this circuit, the value of the current is this ID equal to 2.24 milliamps. Okay? And this was what the exercise wanted, wasn't it? Find the value of ID. We could stop here. We could simply stop here because the exercise only wanted this. But we are going to extend this and try to understand more things. If VGS is equal to 3.76 and VT is equal to 2 volts, thus, of course, VGS is greater than VT. And what does this mean? When VGS is greater than VT, it grants that the channel is open, okay? The channel is open. The channel is open. And how about VDS? VDS is equal to 5.52 volts. VGS is equal to 3.76 volts and VT is equal to 2 volts. We observe that 5.52 is greater than 3.76 minus 2 volts, and this grants that we are working in the saturation region of operation. Then, using this calculation here, we have proved our assumption. We firstly assumed that saturation, the MOSFET was operating in saturation. It could have been operating in triode, okay? If the device had been operating in triode, we would need to calculate it all again, but as we understood that VDS is greater than VGS minus VT, we verified that it is indeed saturation rather than triode. Okay, my friends? And therefore our assumption of saturation holds true. And this is all for exercise number 8. Let's go to exercise number 9 now. Exercise number 9. For the circuit of the figure, determine beta, the values of the current and the voltages of VE and VC, and use the data that VB is equal to 1 volt and VE equal to 1.7 volts. Okay, my friends, this is the exercise. Let's go to the solution. Firstly, we need to understand what kind of transistor we are working with. This is a PNP bipolar transistor. Okay, this is a PNP bipolar transistor. Alright, let's go to the solution, my friends. As VE is greater than VB, okay, the voltage at the emitter is greater than the voltage at the base. That is VBE, B is equal to 0.7 volts. Okay, we normally use this voltage here. VEB is equal to 0.7 volts. Okay, we are going to suppose active mode of operation. All right, it is an assumption. If it holds true, then our calculation is right. If there is any inconsistency in state of active mode of operation, we are going to need to suppose saturation. Okay, as the voltage at the emitter is greater than the voltage at the base, we are going to assume active mode of operation. If so, 10 volts is going to be equal to 5 kilo ohms times IE. Take a look at the voltage drops. 10 volts is going to be equal to this voltage drop here plus VEB plus 100K times IB. All right, the voltage from here to here, okay, this is ground, okay, 0 volts, and this is the supply, 10 volts. Pay attention to the voltage drops. 10 volts is equal to the voltage drop here plus the voltage drop here plus the voltage drop here. Could you guys comprehend? Okay, if so, and manipulating, okay, we use that we find that IE is equal to 1.66 milliamps. Okay, this is what we can find. And how about IB? I forgot to mention that IB, okay, IB is equal to, as the exercise said, VB is 1 volt, IB is equal to 1 volt divided by 100 kilo ohms. Okay, this is the value of IB. IB is then 10 microamps. Okay? I take this value of IB, I use it here. VEB is 0.7 volts, and we solve for IE, and we find 1.66 milliamps. Okay, my friends? Now, using the value of IB, we find IE. And we already found IE. Now we're going to use these values to calculate the other parameters. IE is equal to beta plus 1 times IB, which is equal to beta plus 1 is equal to 1.66 milliamps divided by 10 microamps. Okay? And in this way we find the value of beta equal to 165. The exercise wanted us to calculate the value of beta, and this is the first result. Okay? Firstly, we noticed that VEB is equal to 0.7, and we took a look, we pay attention to the voltage drops from 10 to 0. 10 is equal to the voltage drop here, plus the voltage drop here, plus the voltage drop here, and using the value of IB, we found IE. Okay, and with the value of IE and the value of IB, we find the value of beta. Alright, and this is the first conclusion. Let's continue. We have to find the value of IC now. We have already IE, we have IB. Now we need to calculate IC. IC is equal to beta times IB, and this is equal to 165 times 10 microamps, and this is equal to 1.65 milliamps. Okay? This is the relationship between IB and IC. Beta is 165, and if I multiply this number by the value of IB, we find 1.65 milliamps. Okay? Pay attention to this. Pay attention to this because it is normal. It happens. The value of IC is very close to the value of IE. Then we have the certainty that we are working right, that what we're doing is right. Okay, now let's calculate VC. Let's calculate VC. VC is equal to 5. VC here is equal to 5 kilo ohms. Sorry. 5 kilo ohms times 1.65 milliamps minus 10 volts. Okay? VC is going to be equal to the voltage here. As IC is going downwards, the voltage drop is going to point upwards, and I have a negative source here. Then I add the negative source. Okay? And then I find that VC is equal to negative 1.75 volts. Because of the influence of this negative source, we find that VC is negative. VC is negative 1.75 volts. Had it been the ground, then the value of Vc would be positive rather than negative, okay? It's negative because of the influence of this negative voltage source. Okay, my friends, and lastly, observe that VE is equal to 5 kilo ohms times IE, which is equal to, no, sorry, VE plus 5 kilo ohms times IE is equal to 10 volts, okay? VE plus the voltage drop here is equal to 10 volts, okay? Alright? There is going to be voltage drop in this direction here. Then VE plus this voltage drop has to be equal to 10 volts. And from this step, we find that VE, we have to substitute, okay? We have to substitute the value. IE is equal to 1.66 milliamps, and ultimately we find that VE is equal to 1.7 volts. Alright, my friends, this is all for exercise number 9. Observe that VC is negative, but VE is positive because of the influence of this positive voltage source. Okay? Take a look at them. They look similar, isn't it? VE is positive 1.7 and VC is negative 1.75. They are similar and they are influenced by these voltage sources. And this is all for exercise 9. Let's go to exercise number 10. Exercise number 10 now, my friends. In the circuit of the figure, the collector voltage is negative 4 volts. Calculate the voltage at the emitter such that the current gain is suitable for heavy loads. For example, a DC motor. Okay, my friends, this is the exercise. Let's go to the solution. We are dealing with a PNP transistor. Firstly, we need to identify what kind of transistor we are working with. This is a PNP bipolar junction transistor, okay? Notice that when the gain is said to be very high, the exercise imposed this condition, okay? The gain has to be very high. In this case, when the gain is very high, okay, IE is equal to IC, okay, and beta is negligible. From the circuit, we see that, take a look at the voltage drops, negative 10 volts plus 2.4 kilo ohms times IC is equal to negative 4 volts, okay? Here it is not 24, it is 2.4, all right? And negative 10 volts plus this voltage drop has to be equal to this voltage here, okay? We have a voltage drop here. This voltage drop here plus the voltage of this source has to be equal to negative 4 volts. Alright, my friends, from which we find that IC is equal to -4 minus 10 volts divided by 2.4 kilo ohms, and this is equal to 2.5 milliamps. Alright, this is the value of the collector current, and this is also the value of the emitter current, 2.5 milliamps. Okay, could you see that had it been positive, had it been here positive 10 volts, it would be -4 minus 10 volts, and this would be -6. But here it is -4 minus 10 volts, which is +6, okay, because here the source is negative, here the source is positive, here the source is negative. That's why we did this in this way. We also observed that 12 volts is equal to 5.6 kilo ohms times IE plus VE. Okay, pay attention on the voltage drops. VE plus this voltage drop here is equal to 12 volts. Okay, did you guys understand? Alright, VE plus the voltage drop across this 5 kilo ohms resistor is equal to 12 volts, and from which we get that, and we already know the value of IE is 2.5 milliamps. We need to just substitute and manipulate the expression, and we find that VE is equal to -2 volts. Okay, my friends, this is all the exercise requested from us, and it is all. Okay, and we are going to move on to the next exercise. We are going to go to exercise number 11 now, my friends. Exercise number 11 now, my friends. Find the value of RD and RS so that the drain current is 1 milliamp and the VD is equal to 0 volts. Additionally, the exercise provided this data that we shall use to solve the exercise. Okay, my friends, let's go to the solution. But before calculating, we need to understand what kind of transistor we are working with. This is a MOSFET, a field effect transistor. Okay, the exercise imposed that VD has to be equal to 0. Okay, VD has to be equal to 0. As a consequence, we know that Vs is less than 0. Okay, VD is equal to 0. The exercise imposed that VD has to be equal to 0. As a consequence, the voltage at the source has to be less than 0. Okay? Alright. We conclude that the device is operating in saturation. Okay? The device is operating in saturation because VDS is greater than VGS minus VT. And then we discovered that the condition for saturation is satisfied. Okay, then we are going to use the expressions for saturation. Observe that we can calculate ID in this way. ID is equal to VDD minus VD divided by RD, okay? The voltage at the drain plus this voltage drop here on RD has to be equal to the voltage of the voltage source here, okay? And if we manipulate this, passing one to one side and the other to the other side, we find this expression here. And the exercise imposed that ID is equal to 1 milliamps. Then we find that ID is equal to 1 milliamps. Okay? And we are going to carry out this manipulation to find that RD is equal to 2.5 kilo ohms. Okay, this is the first result. The exercise wanted us to calculate RD and RS. We have already calculated RD. Now we need to calculate RS. As we are working with the device in saturation, this expression is valid. ID is equal to a half of Kn prime W over L VGS minus VT squared. Okay, for saturation, this is the expression that we use for the current. We need to just substitute the values. Kn prime is equal to N COX, W is this, L is this, just using the values, and we find that ultimately, and we have to equal this 1 milliamps. Okay, just to help us calculate everything, if we equal this to 1 milliamps and substitute Kn prime by N COX, W by this value and L by this value, we find that VGS is equal to 2 volts. And since Vg is 0, okay, Vg is equal to 0, VGS is equal to Vg minus Vs, which is equal to 2 volts, and we find that Vs is a negative number, 2 volts. Okay, Vs is a negative number equal to 2 volts. Alright, my friends, and now we calculate the value of Rs. Rs is equal to Vs minus Vs SS divided by ID, and this is equal to negative 2 volts minus 2.5 volts, and this is all divided by 1 milliamp, and this is equal to 500 ohms. Okay, my friends, and this is the value of Rs, and we've just calculated everything that the exercise wanted us to calculate. Okay, my friends, let's move on to exercise 12. Exercise number 12. Consider the circuit of the figure. It is fed by a voltage source Vi of t and has components R equal to 10 kilo ohms and C equal to 0.1 microfarad. The question: what is the transfer function in the frequency domain. Okay, my friends, this is the exercise. Let's go to the solution. Firstly, we need to understand the components of the exercise. This is a capacitor, this is an operational amplifier, and this is a resistor. Okay, we need to be able to work with these components. When the input signal is connected to the negative terminal of the operational amplifier, the transfer function is, okay, VO over VI is equal to negative Z2 of S divided by Z1 of S. Okay, this transfer function occurs when the input signal is connected to the negative terminal of the operational amplifier. Okay, in which Z2 of S is equal to 10 kilo ohms. Okay, and Z1 of S is equal to 1 over SC, and if we use this value here, we find that it is 10 to the 7th over S. Okay, therefore the transfer function is VO over VI is equal to negative R, which is Z2 of S, divided by 1 over SC, and this is equal to negative S times 10 to the 4th ohms times 10 to the negative 7 farad, and ultimately we find that VO over VI is equal to negative S over 8,000. Okay, my friends, this is the transfer function as a function of the complex variable for exercise 12, my friends. And let's go to the last. Let's go to exercise 13. Let's go to the last exercise, my friends, exercise 13. For the circuit of the figure, what is the value of the output voltage if the input voltage is 0.5 volts and R1 1 kilo ohms and R2 100 kilo ohms? Okay, my friends, that's the question. But before calculating anything, let's identify what we are working with. This is a circuit around an operational amplifier with resistances, okay? And this is what we are going to work with. Let's go to the solution. As the input signal is being applied to the positive terminal of the operational amplifier, the transfer function is, okay? Observe that the input signal is applied to the positive terminal of the operational amplifier. Okay, in this case the transfer function is V out over V in equal to 1 plus Z2 of S divided by Z1 of S. Okay, this is the transfer function when we have the non-inverting configuration of the operational amplifier, and in this case Z2 of S is equal to R2 and the Z1 of S is equal to R1. Okay, substituting V out over V in is equal to 1 plus R2 over R1, which is equal to 1 plus R2 is 100 kilo ohms and the R1 is 1 kilo ohms. Okay, we wish to calculate the value of V out. The exercise wanted us to calculate the value of V out. Therefore, V out is going to be equal to 1 plus 100 kilo ohms divided by 1 kilo ohms times the value of the input voltage, 0.5 volts. Okay, and when we calculate this, okay, this is going to be 101 times 0.5 volts, and this is equal to 50.5 volts. Okay, my friends, this is the last exercise. I hope you understood everything and enjoyed the video. My friends, I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye.